Okay, now let's spend some time talking about discrete probability distributions. We've covered the basics of probability, and now we're going to talk about the distribution of a single discrete random variable. And what do we mean by a discrete random variable? Well, we may not be familiar with the term, but it's a concept that we're used to. A random variable is one that can take on different values at different observations, and on any given observation, the outcome that we get, or the value that the variable will take on, is entirely random. And this is true of actually most variables that we observe. Now, a discrete probability distribution, on the other hand, is a listing of all the possible values that a discrete random variable can take, along with the associated probabilities. So we have to have two things. We have to have all the possible values, and for each value, we have to have the probability of getting that particular value. And it can be listed in the form of a table, which is the most common form, or a formula, or a graph, anything that captures the essence of each possible value and the possible outcomes, the probability of each possible outcomes. So let's take the example of rolling a die, and let's see what that may look like. Okay. Well, I've started to put together both the table form and the graph form of this probability distribution. And the key is we've got to capture each of the possible values. And if we're dealing with a die, it's a six-sided cube, and on each surface there's a number of dots, either 1 all the way through 6. So when we roll the die, the side that's facing up is going to have one of 6 possible numbers of dots on that upward-facing face of the die, or surface of the die. So we'll either get a value of 1, 2, 3, 4, 5, or 6. So that's the listing of all the possible values. Now, what about the probabilities? The key here is to recognize what is it that we need to have in order to say we've got a probability. Well, remember our basic criteria. The probabilities have to be values between 0 and 1. Therefore, there will be non-negative, and they have to sum to 1 across all the possible outcomes. So, here's the key. What do I know about rolling a die? If I have an equal probability of of getting each one of my possible values, and the total probability has to sum up to 1, then intuition and logic both tell me that the probability of getting each outcome should be 1/6, 1 over 6, and it should be the same all the way across, assuming I'm dealing with a fair die. So I'll enter those values of 1 over 6 as the probabilities for each of these values, and at the same time we'll see them populated graphically on the chart. So first probability of getting a 1 is equal to 1 over 6, and then I'll copy that all the way down for each of these values. So here I have exactly the same probability of getting each of the 6 values, and they should sum to 1. I'll use my AutoSum function just to check. And yes, they sum to total probability of 1 across all the outcomes. What about the graph? Well, we'd expect each of the possible values 1 through 6 to have exactly the same probability. So here I've just generated a column chart, but we can see that the probabilities are all exactly the same. So graphically or in table form, we can represent the probability distribution. And like all distributions, they can be summarized by a mean value, which we call the expected value in the case of a discrete probability distribution. And we can also summarize it using the variance or standard deviation. So we can come up with a summary measure that captures the central location and one that captures the amount of spread in the data. Well, let's go back to take a look at our graph and our probability distribution. And what would we expect the mean of this distribution to be? What do I mean by that? Well, what I'm saying is, if I were to roll the die 5,000, 10,000 times, and each time I recorded the observation, the number of dots on the upward-facing surface, what would that average be of those values across those 5 or 10,000 or any large number of trials? And here it's a very important distinction to capture. There are two ways of representing the distribution of these values. One is in the form of this probability distribution, where I can list each possible value and then capture the probability of getting each of those occurrences. Or I could actually make observations and generate a list of observations. And we have to treat these differently when we're going through calculations of these summary measures. We're actually more accustomed to dealing with lists of values. In our first block of material, we looked at lists of thicknesses of mica sheets or fast food service times, and those were lists of observations. We're used to making observations by actually doing some kind of measurement or counting on some sample. Well, that's one way of sampling from a population and listing those values. Another way of capturing, if we have a variable that is that we can model by a discrete probability distribution, it turns out that if we capture this distribution with each value and the probability of each value, we really capture the essence of that same very long list of values, actually more accurately than if we just took a sample of observations from such a distribution. And as I said, the approach that we need to take to calculating the summary measures is different in each case. We saw in block 1 how we generate summary measures, how we can calculate the mean, calculate the variance and standard deviation from a list of values. But when we're dealing with just a probability distribution, we have a slightly different challenge facing us, because just a list of values here, 1 through 6, doesn't capture how often each one shows up. It doesn't capture the relative likelihood. That information is captured in the probabilities. So we have to take those probabilities into account. Now, let's think about our probability distribution for the outcomes of rolling a die. And in this case, we can think of where our average value might be. Suppose we said we want to find the average of this distribution, and we were going to do it by summing each of the values and dividing by the number of occurrences. So I'm going to say equals sum of these values 1 through 6 divided by, and I have a label in here for the that column of data, divided by the number of occurrences, which is 6. I get a value of 3.5. Now, firstly, we may notice 3.5 is not one of those possible values, but it should not be too disturbing to us, because even though our variable is discrete, the mean of that distribution can take on a value that's not one of the possible values. And that may seem counterintuitive, but in a practical sense, an example that comes to mind is thinking of the average number of children in a household in the United States. It's been at values of 2.5, 2.2, maybe now it's 1.8, but rarely is it quoted as an actual whole number, and certainly that would be a numerical discrete variable. So that shouldn't disturb us. If we look at the graph, does that number make sense? If we think about the mean of the distribution as sort of the balance point of the distribution, then we'd expect this distribution to balance, since it's a uniform distribution, somewhere right between the values of 3 and 4. So 3.5 is a good intuitive and practical value for us, and it turns out that is the correct value in this case. However, supposing we had a die that was not a fair die. Supposing we had a die for which the likelihood of getting an outcome of 6 was twice as much as the likelihood in each of the other cases. So whatever the probability it was of getting 1 through 5, those were the same, but the probability of getting 6 was twice as high. Well, if we ponder this for a while, we'd recognize that the probabilities change in this case. In the case of the values 1 through 5, our probability would actually equal 1 over 7. And when we get down to the outcome 6, that probability would be twice as much. It would be 2 over 7. And again, we can verify that those values sum to 1. So we're happy with that. And the graph also shows that things make sense. We have a probability of getting a 6 is twice as much as the probability of getting the other values, 1 through 5. Okay, well, let's think about this for a moment. Intuitively, would we expect from the graph that the mean would be at the same value, 3.5, or would it shift? Well, again, using the concept of the mean as the balance point of the distribution, certainly that mean would have to be at a higher number than 3.5 in order to balance out that extra weighting, if you will, of the higher probability of getting a 6. So 3.5 certainly can't be the right value in this case. However, if we took the average using the approach of summing up the values 1 through 6 and dividing by 6, then that's the number that we're going to get, 3.5. And as we can see here, that's clearly not correct. It turns out when we get around to calculating the mean or the expected value for a discrete probability distribution, we really have to take a different approach to finding this value. The expected value, or the mean of this discrete probability distribution, is really captured as the weighted sum of the possible values. So not the average anymore, the arithmetic mean. That won't work in the case of a discrete probability distribution. Here what we've got to do is something called a weighted sum. We're going to take each one of the possible values, weight it by multiplying it by its probability of occurrence, and then we're going to sum those products together. So we take each value, we're going to weight it by multiplying it by the probability, and then sum those products together. And in mathematical formula, it looks like this. Again, each value, v sub I, multiplied by the probability of getting that value v. And then we sum those products across all the possible values of I. So in this case, for our die, where we've got values 1 through 6, we would take the first value and multiply it by its probability. Then the second value, multiply it by its probability, etc. And we end up with a weighted sum that is going to be different from 3.5. And it turns out Excel has a formula that's very handy for doing exactly that calculation. It's going to take, for two columns of equal size, two arrays of equal size, it's going to take the product of each pair of values and sum them up. And that's really what we want to do here. And the formula is called the sum product. So I'm going to take the sum product of my values and my probabilities, close parentheses, and I get a value of 3.86. So it certainly has shifted up to a higher value than we would have gotten had we simply taken the arithmetic mean. So I use this just to illustrate the fact that when we're dealing with a discrete probability distribution, it's really important that we shift our thinking from using the concept of an average or an arithmetic mean. We now have to take all of our definitions for everything, for average, variance, standard deviation, covariance, all of those definitions that are rooted in an average in some way. We have to just replace that idea with a weighted sum. We'll still follow the rest of the definition, but now we're going to use a weighted sum where each value is going to be weighted by its probability to capture its relative frequency in the distribution. And then we sum those products using the sum product formula, and that'll give us our weighted sum, our actual expected value in this case for our distribution. So what about the variance of a discrete probability distribution? Again, it's a measure of the variability of the distribution, just like it was when we dealt with our observations, our list of observed values. And the definition in general is still the same. We still find the variance as the average of the squared deviations. The difference here is how we interpret the word average. We're not going to take the arithmetic mean, but we're going to take the weighted sum of the squared deviations, where each deviation is weighted by its probability. So, for a variable x, mathematically we can display it this way. We take each value, we find its deviation by subtracting the expected value, And then we square that to get the squared deviation. The squared deviations are then multiplied by the probabilities, and for every pair of values and probabilities, those products are added together across all the values, and that's going to give us our variance. Standard deviation always is going to be the square root of the variance, so we simply take the square root in the same way that we would have before. So now, just by shifting our thinking from an arithmetic mean to this concept of a weighted sum, we can now calculate all of our typical summary measures for a discrete probability distribution, just as we did for a list of observed values. And let's take a look at this for a problem that comes out of your text. And we'll take a look at problem 540, and it's on page 245 of the text. And you have no data file for this, but we will sort of make things up as we go along in a blank spreadsheet. So we're given some information in the problem that says that a typical customer buys a random number of polo shirts when he shops at a men's clothing store. And you're given the distribution in words. You're told that the probability that x equals 0 is 0.3. The probability that x equals 1 is 0.3 again. Probability that x equals 2 is 0.2. And then for x equals 3 and x equals 4, in each case the probability is 0.1. And again, we can easily verify that those probabilities sum to 1. And then we're asked to find the mean and standard deviation of x, of the number of polo shirts that a customer buys in the store. So let's see. Our expected value is, and I've actually created some placeholders down here to put some of these answers. Our expected value of x, the mean of this distribution, is going to be the weighted sum of each of these values of x, the variable, where in each case we're going to weight it by the probability. So we'll say equals sum product of our values of x, 0 through 4, comma, our values of the probabilities. And I hit enter. And I get a mean of 1.40. So that's long term. If I look at the average number of shirts purchased by each customer over a long term period, over a large number of customers, it would be on average 1.4 shirts per customer. And you could verify this by taking each of these pairs of values and multiplying them together and then adding those products. And you'll see you get the same value that the sum product formula from Excel gives you. What about the standard deviation of x? Well, the standard deviation is always going to be the square root of the variance. So let's calculate the variance off to the side. And the variance is going to be the weighted sum of the squared deviations of the values. So first I need to find deviations. I'll abbreviate it DEVS, but in each case the deviation is going to be the value of x minus the expected value. And I'm going to copy this formula down, so I'll just lock in that cell location. So I'm going to copy this down for each of the values of x, of my number of polo shirts purchased. And in each case I now get the deviation. Some of the values are negative if x is less than the mean. If x is greater than the mean, the deviations are positive. That's fine. But the variance now requires me to find the squared deviation. So I will create another column here called squared deviations. And in each case, I'll take the deviation value I found and raise it to the power of 2 using this little caret symbol, little upside down V that's above the number 6 on my keyboard. And I'll copy this formula all the way down again. So now I have the deviations and the squared deviations. And you'll notice that the squared deviations are all positive because those negative deviations resulted in positive squared deviations. And the variance now is going to be the weighted sum of the squared deviations, where in each case I'll weight the squared deviation by the probability of that squared deviation showing up. So once again, I'll use the sum product formula. and I'll capture my column of squared deviations, comma, my probabilities. For these calculations on discrete probability distributions, we'll always be weighting things by the probability of occurrence. So I get a value of 1.64. I have to remember that's my variance value. My standard deviation is always going to be the square root of the variance. And I get a value of roughly 1.28. Okay, so here we're able to calculate the mean and the standard deviation of this discrete probability distribution using this concept of the weighted sum, both to find the mean and to find the variance. And from the variance, we find the standard deviation. Let's talk a little bit about what happens when you add or multiply a constant times a value, because as we continue on in problem 40, it says, suppose each shirt costs $35. Then come up with some new variable y, which is the total amount of money in dollars spent by a customer when he visits the clothing store, and you're asked to find the mean and standard deviation, not of the number of shirts purchased now, but of the amount spent. So we could do it this way. We could say dollars spent, and if a customer comes in and buys 0 shirts, that dollar spent is going to equal 0 times the $35, which is the cost of a shirt. And I'm going to lock in that cell location. So I get 0, which is represented here as a dash. And then if 1 shirt is purchased, the amount spent is $35, then 70, 105, 140, etc. So here I really have a probability distribution of the amount of money spent. This would be my variable y. Whereas, again, I have my initial variable x. And I have the amount spent and I have the probabilities. So this is a legitimate probability distribution as well. And if I wanted to find the mean of y, I could find that using, again, the sum product of my dollars spent, comma, my probabilities. And I get $49. Well, there's something else that can help us here, because in each case we're multiplying the number of shirts purchased by a constant. What do we know about a constant? Well, what's the expected value or the mean of a constant? Well, if it's a constant, it's always constant. So that expected value is going to be whatever the constant is. What about the standard deviation? What about the variability or dispersion of a constant? Well, if it's a constant, it's a constant. So it has no spread or variability. Its standard deviation is 0. And if we use these two ideas, they can help us understand how we could save ourselves a little bit of trouble if we're adding or multiplying a constant value times some discrete probability distribution. And these are captured in something called the laws of expected value, or the laws of variance and standard deviation. So just to sum up, for any distributed variable x and a constant c, the expected value of that constant times x is just going to be that constant multiplied by the original expected value. And we see this example immediately in this problem. Rather than, here's another way I could have done this. Instead of calculating my expected value by using the sum product formula, first calculating this new variable y, dollars spent, and then finding the expected value, I could simply have said, hey, if my expected value of the number of shirts purchased is 1.4, and each shirt costs $35, then my expected value of the dollars spent is just going to be that expected value of the number of shirts purchased multiplied by the cost of each shirt. And I get, once again, exactly $49. Similarly with the standard deviation of y. For, again, a variable, distributed variable x and a constant c, if I have a constant added to a variable x, then the variance doesn't change. I'm just moving my my central location positive or negative. So my variance and standard deviation don't change. But if I'm multiplying the constant times x, then my variance is going to change by a product of my constant squared, because remember the variance has those squared terms in it. My standard deviation, however, is just going to be my constant times my original standard deviation. So the same thing applies. We could calculate the standard deviation of y the long way, finding square deviations, etc. Or we could use that law of standard deviation once again and say that the standard deviation of my dollars spent would just be my standard deviation of my number of shirts purchased multiplied by, again, that constant $35. And I'll leave it to you to verify that this is the same result you would get if you calculated deviations and square deviations for y and went ahead and found the variance and so on the long way. So the laws of expected value and laws of standard deviation are, in a way, shortcuts for us once we know that we have a constant either being added or multiplied by our discrete random variable. And then lastly, in this problem, we're asked to compute the probability that a customer's expenditure will be more than one standard deviation above the mean. Well, I'll use my values I got sort of with the laws of expected value, laws of standard deviation approach, or the shortcut approach. And I'll say, hey, what's the mean plus one standard deviation? Well, that's going to be $49 is the mean, plus one standard deviation is $44.82. So I get $93.82. And I can say, well, what's the probability, based on my variable y, that I would have a value that's greater than that? Well, the only values greater than that are 105 and 140. And I have the probabilities of each of those occurrences taking place. So all I need to do is to sum the probability of getting 105 with the probability of getting 140. Remember, in this case now I'm adding probabilities. I'm not adding my dollar values. And I get a probability of 0.2. It turns out, by the way, that if I recognize that one standard deviation above the mean for my dollars spent is actually going to correspond to one standard deviation above the mean on my number of polo shirts, we can actually get to this answer a different way. If I think about it, actually I'm going to take these values and drag them over here to column y. But if I were to think of my mean plus one standard deviation as being my mean of my variable x plus one standard deviation, I get a value of 2.68 shirts. What are the values that are above 2.68 shirts? Well, once again, it's going to be 3 shirts or 4 shirts. And again, I'd be adding the probability of being more than one standard deviation over the mean. I'd be adding the probability of getting 3 polo shirts plus the probability of someone purchasing 4 polo shirts. And I would get exactly the same answer for the probability of being at or above one standard deviation over the mean. All right, that wraps up our discussion on manipulating discrete random variables and discrete probability distributions from the standpoint of calculating some of the basic summary measures, the expected value, the variance, and the standard deviation.